Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a fascinating paper published January 31st, 2025, titled 1. Simple Test Time Scaling. This paper explores a really neat idea called test time scaling, which is all about using extra computational power to improve a language model's performance when it's actually being used, not just during its initial training. They achieved this with two main ideas. First, they built a small, high-quality dataset of 1,000 challenging questions paired with reasoning traces. These are like the step-by-step thought processes to reach the solution. Second, they developed something called budget forcing, a method to control how much the model thinks at test time, sometimes even prompting it to wait and reconsider, which can lead to better, more accurate answers. Alright, so as we've heard, these methods like budget forcing and those detailed reasoning traces are pretty central to improving the model's performance right when it's needed. And for those of you interested in the nuts and bolts, well, the authors have generously made their GitHub repository public. This repository is a great resource containing all the code for this work. You'll find scripts for evaluation. That's how they measure the model's performance. Data creation scripts and the training scripts. Plus, importantly, the inference code. That's the programming that actually runs the trained model to get answers. And even the visuals from the paper are included. Okay, so this first figure really helps us visualize that test time scaling concept with their S132B model. We're looking at three different plots, each representing a tough reasoning benchmark, mathematical problem solving, competition math, and PhD-level science questions. The horizontal axis shows the average thinking time in tokens. Tokens are essentially the units of text, like words or parts of words, that the model processes when it's thinking. And the vertical axis shows accuracy. What's clear across all three is that as the average thinking time in tokens increases, the model's accuracy also tends to go up. This demonstrates how allowing more computation at test time, managed by things like budget forcing, can improve results. Okay, so Figure 2 digs a bit deeper into what makes this S132B model tick. On the left, you can see a whole cloud of different topics, like mathematical logic, computer science, and even things like economics, all part of that diverse S1K dataset they carefully created. This dataset was then used for supervised fine-tuning, or SFT. Supervised fine-tuning is a process where an already trained model is refined further on a specific, smaller dataset, in this case, S1K, where the correct answers or solutions are provided. And the right side of this figure really shows the power of this approach, illustrating the S132B model's sample efficiency. Basically, how well it learns from relatively few examples. It's achieving high accuracy with just those 1,000 S1K samples. Alright, so we've seen how that diverse S1K dataset is used for supervised fine-tuning. Now, Figure 3 gives us a really concrete example of how that budget forcing technique actually works in practice with the S1-32B model. Here, the model is asked, how many are in Raspberry? Initially, its reasoning trace, that step-by-step thinking we talked about, leads it to say there are 2. But then, budget forcing kicks in. The system suppresses the model's attempt to finish by stopping its end-of-thinking token, which is like a special signal the model uses to say, I'm done thinking, and instead appends, wait. This prompts the model to reevaluate, correctly find 3 R's, and even acknowledge its initial mistake in the final response. Okay, so after seeing budget forcing in action with that Raspberry example, this next figure, Figure 4, gives us a broader look at how different test time scaling approaches compare. On the left, in plot A, we're again looking at sequential scaling via budget forcing, similar to what we saw in the first figure. This plot focuses on the AIME 24 competition math problems, and it highlights how specifically ignoring the model's end-of-thinking token, that signal that it's done, and adding wait helps push accuracy up as the average thinking time in tokens increases. Then, plot B on the right introduces a different strategy called parallel scaling, using a technique known as majority voting. With majority voting, well, the system gets the base model to generate multiple different reasoning attempts for each question, and then the final answer is chosen based on what appears most often. For these PhD-level science questions, you can see that sequential forcing with the S1 model still achieves a higher accuracy, around 60%, compared to this parallel majority voting approach with the base model. Okay, so we've seen how different scaling methods work. Now, Table 1 here really benchmarks the S132B model against a range of other models. We're looking at scores on tasks like AIM 2024, Math 500, and GPQA Diamond. These are all challenging reasoning tests. The key thing is that S1 to 32B, when using budget forcing and trained on just 1,000 examples, achieves 56.7% on AIME. That's a solid improvement from the 50% it gets without budget forcing. And while some other open models like R1 get higher scores, they were trained on vastly more data, around 800,000 examples, highlighting how sample-efficient S132B is. Alright, so we've established that S1 to 32B is pretty sample-efficient. This next table, Table 2, really digs into why its S1K training dataset is so effective, using what are called data ablation studies. An ablation study, in this context, means they're testing different ways of creating that 1,000 sample dataset by looking at what happens if you remove certain parts of the selection strategy. We see performance on AIM, Math, and GPQA. The results show that simpler methods, like randomly picking 1,000 examples or focusing only on diversity or problem length, lead to significantly worse scores than the curated S1K. Impressively, S1K performs nearly as well as training on the full 59,000 examples, really underscoring the power of its careful curation. Okay, so we've seen that the S1K dataset is really well put together. Now, this next table, Table 3, dives into how they settled on budget forcing as their go-to method for scaling test time compute, which is the amount of calculation the model does when it's actually trying to answer a new question. This table shows another set of ablation studies, this time focusing on the AIME 24 task, comparing different methods to control how much the model thinks. We see metrics like control, basically, how well the method limits thinking tokens, scaling, which shows how much accuracy improves with more thinking, and performance, the top accuracy. Budget forcing, which we've discussed, that technique of sometimes adding weight to prompt more thought, clearly wins, with perfect control and the highest performance of 56.7%. Other approaches, like rejection sampling, where the system generates several reasoning attempts and then picks one or discards others, actually showed worse results with more thinking time. It's clear that budget forcing really stands out as an effective way to scale how much these models think at test time. The main takeaway here is that through smart dataset curation, like with the S1K dataset, and clever techniques like budget forcing, we can achieve impressive reasoning from models without needing overwhelmingly large training datasets. This is really important for making powerful AI more accessible and efficient. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.